Okay, let's start the diagonalization of the matrix. So actually this is the section 5.3. So from the 5.1, 5.2, and 5.3, we've talked about the eigenvalue and eigenvectors, right? So in this section, we will talk about how to use the eigenvalues, eigenvector to decompose arbitrary matrix A. Okay, so let me start. So first of all, the scale matrix A is said to be a diagonalizable if the matrix A is similar to the diagonal matrix, that is something like this. So if you remember the definition of the similarity between the two matrices, as you can see here, if the matrix A and matrix D are similar if there exists the matrix P, something like this, right? So this is the definition of the similarity, right? So if you can go back to this here, right? Here was the definition, right? So for some the invertible matrix P and for some diagonal matrix T, right? So in other words, by using the invertible matrix D, matrix P, and some diagonal matrix D, we can decompose arbitrary matrix A, something like this, right? So so far we've talked about several kinds of the decomposition method, right? What was that? First of all, we've talked about LU decomposition. Okay, let's LU decomposition. And there was the QR, right? QR decomposition, something like this. And today we talk about PDP negative, so diagonalization. So I strongly suggest you to summarize these kinds of the transformation and our decomposition method and compare the property of each one, right? So you have to understand the concept. So anyway, today we will talk about the diagonalization. Actually, this diagonalization can be done by Eigen Vectors and eigenvalues, eigenvectors, eigenvalues. Okay, so let's discuss this one. Okay, so here is theorem. Here is a very important theorem, diagonalization theorem. So first of all, n by m matrix A is diagonalizable if and only if matrix A has a n linearly independent eigenvectors. In other words, if matrix A has a n linearly independent eigenvector, then matrix A is diagonalizable. Then we can represent the matrix A something like this, right? In fact, A is equal to PD inverse P with the diagonal matrix D if and only if the columns of the P are n linearly independent eigenvectors of the matrix A. In other words, if there exists the n linearly independent eigenvector, then we make a vector P that consisting of this linearly independent eigenvector. Then we can decompose this matrix A as a P times T times inverse P. So it is called the diagonalizable, right? So these two statements are equivalent. In this case, the diagonal entry of the D eigenvalues of the matrix A that correspond to the eigenvectors of the P. So in other words, okay, if matrix A has n linearly independent eigenvectors, something like V1, V2, like Vn, and let's say its corresponding eigenvalues as a lambda 1, lambda 2, and lambda n, then we can decompose this matrix A as a P T P minus, when P is the columns of the P are n linearly independent eigenvectors. So in this case, V1, V2 through the Vn time diagonal matrix D, lambda 1, lambda 2, lambda n with the inverse V1, V2, Vn inverse, right? So in this case, this is the matrix P, this is the matrix D, this is the matrix inverse P, right? So in other words, if matrix A has the n linearly independent eigenvectors, then with the corresponding eigenvalues, then we can decompose this matrix A as the matrix of the matrix P that consists of the eigenvectors with the diagonal matrix D that consisting of the eigenvalues on each diagonal term, right? So this is the diagonalization theorem, or this is called the Eigen Decomposition. So I want to call this one is eigenvalue decomposition, Eigen Decomposition, to compare LU decomposition, QR decomposition, right? So this is the Eigen Decomposition. So in many application that use that is based on the linear algebra, can be easily solved by this diagonalization theorem. So if the matrix A is really hard to understand, but if we can represent this matrix A as this eigenvalue decomposition, then we can easily understand each property and use this diagonal matrix D to make the computation tractable. Okay, so this is the diagonalization theorem. So in other words, matrix A is diagonalizable if and only there are enough eigenvectors to form the basis of the Rn space. So in this case, the n eigenvectors, right? So we call such a basis an eigenvector basis of the Rn space, right? So first of all, let's prove this theorem first. So yeah, actually the proof of this one will take some 3 pages, so it might be confused, but don't worry about it. Just follow the step by line by line and step by step. So okay. So first of all, the matrix P is a n by n matrix with the columns V1 through the Vp, right? It was the definition, right? And the matrix D is the diagonal matrix with the diagonal entries lambda 1 through the lambda n. Then first of all, we can represent the A times P as A times the matrix P, like this, right? This is the definition of the matrix P. Then we can easily compute these two matrix multiplication, something like AV1, AV2, and AVN, right? And we can also compute the P times D as a P is here, diagonal matrix here, right? Then how can I compute this one? because the matrix P is the V1 through the Vn, then we can easily compute this column with this matrix, this every row, right? In that case, we can generate the lambda 1 times V1, right? And this column will generate the lambda 2 times V2. Finally, this column generate lambda n times Vn, right? And now suppose the A is diagonalizable, then A can be represented P times T times inverse P, right? So it is equivalent, right? Then write multiplying this relation by P here, by multiplying P here and here, we can generate the AP and BPD, right? Because P inverse P is equal to I, right? So we have the AP is equal to PD. AP is equal to PD. Then, okay, let me say this is the equation 1 and equation 2. Then in this case, A1 and A2 imply that because these two matrix should be same, so AV1 and lambda 1 V1 should be same, and AV2 lambda 2 V2 should be same, and AVN lambda n Vn should be same. So these two matrices are same, so we find out this kind of equation, right? So, and what else? Since the matrix P here, matrix P is invertible, each column vector, each column V1 through the Vn must be linearly independent. Why? By invertible matrix theorem. Invertible matrix theorem. Also, since the columns are non-zero, why? Non-zero. Why? Because this is eigenvalue, eigenvector. Equations show that the lambda 1 through the lambda n are eigenvalues, and V1 through the Vn corresponding eigenvectors. Right? So we can say that in here, if the matrix A is diagonalizable as P times T times P minus 1, the columns of the P are n linearly independent eigenvectors, and the matrix T consisting of the eigenvalues corresponding to the eigenvectors, right? So yeah, it is that. And finally, given the n eigenvectors, V1 through the Vn, use them to construct the columns of P, use corresponding eigenvalues, lambda 1 through the lambda n, to construct the D. By equation 1 through the 3, okay, let's say this is the 3. We know the AP is equal to P times D, right? In fact, so if the eigenvectors are linearly independent, then P is invertible, right? Then AP is equal to PD will be transformed to will be casted as A is equal to PD P inverse, something like this. So that's what we want to know. So to summarize, the linearly independent eigenvectors and eigenvalue can make the matrix A into decomposed matrices as P, D, and inverse P, right? So this is the diagonalization theorem. So it's very easy. So okay, so let's diagonalize the matrix. Okay, so let's use the diagonalization matrix to find out the diagonalization or the eigenvalue decomposition. First of all, we have a matrix A. Then we want to decompose this matrix A as a P times D times inverse P. Then how can we do that? First of all, we have to find out the inverter matrix P and diagonal matrix D, right? Then we already know what is columns of this inverter matrix P. Eigen Vectors. Whose diagonal of the diagonal entries of this diagonal matrix D is the eigenvalues. It means that we have to find out the eigenvectors and eigenvalues for this matrix A, right? This matrix A. So let's do that. So okay, so first of all, there are several kinds of ways to solve this problem, but we want to use the first step to implement the to use the diagonalization theorem. So first of all, we can find out the eigenvalues of the matrix A and linearly independent eigenvectors of the matrix A corresponding to each eigenvalues, right? If we have the eigenvalues and eigenvectors, then we can construct the matrix P by using the eigenvectors, right? And then what is the matrix D? Matrix D is just the eigenvalues, right? On the diagonal terms, right? And then we can just decompose this matrix A as a P times D times P minus 1. Okay, it's very easy. So let's do that step by step. First of all, how can I find the eigenvalues of the matrix A? How can I do that? We can use the characteristic equation. What was the characteristic equation? Determinant of the A minus lambda I is equal to 0, right? So first of all, because this matrix is a 3 by 3, so we already know that this is a cubic polynomial. It's just a cubic polynomial. So first of all, this one 1 3 3 negative 3 negative 5 negative 3 3 3 1. Then with the lambda I term, it will be lambda here, lambda here, lambda here, right? Then you can easily find out the determinant of this one, right? So please derive this one, because we've already talked about the finding the determinant of the 3 by 3 matrix, right? So let's do that. Anyway, by estimating the determinant and where's that? Yeah, and we can decompose this determinant term as a polynomial term, a polynomial equation. So in this case, negative the lambda 3 square with 3 times lambda 2 square plus 4. Then we can factorize this term as something like this, right? We already know how to do this, right? It is called in Korean 인수분해, right? You can easily do that, right? Anyway, so by factorizing this polynomial term, something like this, we can easily find out eigenvalues. In this case, lambda is equal to 1 and lambda is equal to -2. That satisfies this equation, right? Okay, so it's very easy. First of all, we found the eigenvalues of the matrix A, okay? And then let's find out the eigenvectors. So how can I find the eigenvectors? How can I find the eigenvector? So first of all, when lambda is equal to 1, the equation matrix A 1 times x like this, right? So the eigenvector should satisfy this equation, right? So in other words, A minus just I, because the lambda is equal to 1, right? Actually, this is just a homogeneous equation, right? Then how can I find the solution here? How can I find this one? We already know the matrix A is something like this, right? What is A? 1, 1, 3, 3, -3, -5, -3, 3, 3, 1, minus 3, 3, -3, -6, -3, 3, 3, 0, this, right? How can I find the solution? Something like this. How can I do that? How can I find this? We can easily do that. How can I do that? By row reducing this matrix, then we can represent the vector x as a x1, x2, x3, something like this. So please derive this term yourself. Anyway, so if we find out the solution of this one, the basis of this solution will be the v1 is equal to 1, -1, just 1, right? What about the lambda is equal, when lambda is equal to -1, -2? Then in this case, lambda plus 2I vector is equal to 0, right? If we find the solution of this equation, the basis of this solution will be this one and this one, right? So we can easily check the v1, v2, v3 is a linearly independent set, So how can we do that? By just computing the dot product of each other, right? Linearly, it's not a, sorry. So to check this set is the linearly independent set. We can v1 and v2 and v3 are all 0. When only v1, c1, c2, c3 are 0 to satisfy this equation, then these three vectors are linearly independent. Okay, so now we have the eigenvalues, eigenvectors. Then by using these eigenvectors, we can build just build the matrix P like this. But actually, we can use any order of the vectors, right? Let me say we can just make the matrix P as a v3 to 1, or v2, v3, v1, right? But in here, just to use the disorder, but carefully we have to find we have to make a diagonal matrix T corresponding to the order of this matrix B, matrix V, right? And what's the V1? V1 is here, V2 is here, V3 is here. So V1, V2, V3, or something like this, right? And then we can easily construct the matrix D from the corresponding eigenvalues. So because we have the eigenvalues 1 and eigenvalues -2 here, so final eigenvector matrix D is something like this. Okay. So in here we can represent the matrix A 1, 3, 3, -3, -5, -3. 1, 3, what's that? -3, -5. One. Okay. And P is equal to 1, -1, 1. 1, -1, 1. -1. 0, -1, 0, 1, and T is equal to 0, 1, 0, -2, 0, 0, 0, -2, right? Then matrix A is equal to P. What's that? What's that? Here, right? P, T, and P, -1. So, yeah, this is the eigenvalue decomposition, eigen decomposition of the matrix A into the matrix P and matrix T. Okay, so this is the diagonalization of the matrices. Okay, so in other words, if you can find out the eigenvalues, eigenvectors, you can easily do that, right? So yeah, don't worry about too much. So here's one more theorem. An n by n matrix with n distinct eigenvalues is diagonalizable. Okay, so in this example, there was the okay, so it was the 3 by 3 case, but there's only two distinct eigenvalues, right? But if there are n distinct eigenvalues, in previous case 3, then it is definitely diagonalizable. We can easily show this theorem. So how can we do that? So let's say V1 through the Vp, Vn is eigenvectors corresponding to the n distinct eigenvalues of the matrix A, corresponding to the n distinct eigenvalues of the matrix A. Then we already know the V1 through the Vn are linearly independent. Why? In the lecture 13.1, we've already talked about this theorem here. Not here. No, here, right? So distinct eigenvalues, if we have the distinct eigenvalues, then the eigenvectors are linearly independent. So we already know. So V1 through the Vn is linear. If V1 through the Vn is linearly independent, then the matrix A is diagonalizable by the diagonalization theorem. By diagonalization theorem. Here, if the matrix P are linearly independent, then matrix A is diagonalizable. Okay. So as you can this theorem, we already know if the matrix A has the n distinct eigenvalues and eigenvectors, we can just decompose this matrix A as P P inverse, right? But as you can see here, as you can see this example, even though there is no n distinctive eigenvalues, we can still decompose this one. We can diagonalize this matrix, something like this, right? So if this necessity is satisfied, we can just say that this matrix A is diagonalizable, but even though the matrix doesn't have the n distinct eigenvalues, we can still decompose this matrix A as a diagonalized matrix. Okay, so let's think about let's summarize this one. But to derive this one, there are very long theorem. Actually, in here, we want prove this theorem, but we can just use this theorem. So in your case, you can also just understand what's the meaning of this theorem. Okay, so here's the theorem. Let's say matrix A is a n by n matrix whose distinctive eigenvalues are lambda 1 through the lambda p. So in this case, p is smaller than. So in this case, we can derive the several kinds of property. First of all, if the k is larger than 1 and smaller than p, the dimension of the eigenspace for the lambda k is less than or equal to the multiplicity of the eigenvalues of the lambda k. So what's the meaning of this one? So when you think about the characteristic equation, there are some terms, something like okay, let me say something like blah 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 with some okay, so multiplication. Okay, let's use the A notation A, something like this. Okay, so this is the characteristic equation or the characteristic polynomial, right? In this case, the eigenspace of this one is less than or equal to the multiplication. So if A is equal to 2, the dimension of the eigenspace less than or equal to multiplication 2. So let's see this example. In this case, multiplicity of the lambda is equal to -2 was 2, right? Just 2, right? So in this case, the number of bases, dimension is the number of bases, right? So number of bases should be, in this case, 2, but it will be less than 2. But in other words, the number of bases, dimension or the number of bases of the eigenspace less than or equal to multiplicity. Okay. And the matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspace equal to n, and this happens if and only if the characteristic polynomial factors completely into linear factor. Dimension of eigenspace for each lambda k is equal to multiplicity of the lambda k. So what's the meaning of this one? Sum of the dimensions of eigenspace is equal to n means in this case, this is this is a basis for the eigenspace when lambda is equal to 1. These two vectors, v2 and v3, is the basis for the eigenspace when lambda is equal to -2. Then in this case, the number of bases is equal to 3 in this case. So in this case, in this case, the matrix will be diagonalizable. So even though we don't have the enough distinct eigenvalues, as you can this example, because they only have the two eigenvalues, but if there exists three distinct eigenvectors, then we can say that this is diagonalizable, like this example. Okay. And then one more thing is that if matrix A is diagonalizable and pk is the basis for the eigenspace corresponding to the pk for each k, then total correction of the vectors in the set form the eigenvector basis for the Rn space. So what does it mean? So as you can see here, the set of this one, and this one is just the eigenvectors of this matrix A, right? So it means that those the set of this whole kinds of the vectors can be used to build the matrix P, right? So in other words, by using this theorem, we can just say that even though we don't have the enough number of the eigenvalues, then we can still decompose this matrix A if some conditions are satisfied, something like this and this. Okay, let's see the example. The problem is something like this. So diagonalize the following matrix if possible. Okay, so first of all, this is the diagonal matrix. So we know that we can easily find out the what's that, eigenvalues of this matrix, right? How can you do that? First of all, lambda I should be 5 minus lambda, 5 minus lambda, 3 minus lambda, 0, 1, 4, -1 and 2, 0, 0, 0, 0, 0, 0 here, right? Then determinant of a minus lambda I will be just 5 minus lambda, 5 minus lambda, -3 minus lambda, -3 minus lambda, right? So we know that lambda minus 2 lambda plus 3 제곱, and the eigenvalue should be 5 or -3, right? 5 or -3 here, each with the multiplicity 2. Okay, and then we can find out the basis for each eigenspace. So for example, when lambda is equal to 5, then A minus the solution, the basis for solution of this equation will be something like this and this. You can do this one, right? And for lambda is equal to -3, you can also find out the solution of the A plus 3 lambda x is equal to 1. So V3 is something like this and V4 is something like this, right? So even though there is only two eigenvalues, but the sum of the basis for each eigenspace, in this case 2, in this case 2, so the total number of the eigenvectors is 4, right? So because this is a 4 by 4 case, then we can say that this matrix A is still diagonalizable with the matrix P, something like this. In this case, it's just P3, right? And matrix T as a diagonal matrix. So in this case, the P is equal to V1 and V2 here and here, and V3 and V4 here and here, and matrix B should be 5, 5, because there is a 5 and negative 3, so negative 3 here, right? So in other words, we can decompose this matrix A into the matrix P, D inverse P. Okay. So yeah, in this section, in this chapter 5, we've talked about what is the eigenvalue and eigenvector. Then how can we use this eigenvalue, eigenvector to decompose the matrix A into the diagonalizable matrix. So something like this, right? So actually, it is very, very important decomposition method. So actually, this semester is almost done, but next week we will talk about the SVD, singular value decomposition. There exists one more decomposition method, but actually SVD method, singular value decomposition method, is just the extension of the eigenvalue decomposition here. So it means that we almost done. So okay, so let's do that. So please remember that we have the final exam in 2 weeks. So please study the linear algebra things and this semester courses as soon as possible. Okay, thank you very much.